Yeah, we're live on YouTube. Yeah, we're live on YouTube.
Good evening. Welcome to the Tucson Amateur Astronomy Association monthly general meeting. We generally meet on the first Friday of the month, except occasionally when there's a holiday. I want to welcome all of you here in the room. We have members here in the room. We have members on Zoom. And we've got visitors on social media joining us tonight. And we've got a very interesting night ahead. We've got Bob Rose helping us on camera tonight. And of course, Terry Lappin on general multimedia stuff that she does. Always appreciate the work they do to bring this to you. They also will help bring this to the internet, and it'll be available on our website for the future if you want to come back and listen to some of the things that you hear tonight. We always try and bring you cutting edge. We're very fortunate to have here at the University of Arizona great minds working in astronomy, and associated with this great astronomy town. We have lots of other groups, including one that's across the street. And tonight we're going to have a presentation that's going to tell us about the Vera Rubin. It has been a long time coming. You all, I'm sure, have seen this first release of images from the telescope. Tonight we have our very own Ardis Herrold, a longtime member who came to Tucson to work with the Vera Rubin project. She, like many of us, were inspired in astronomy as a young child. She's been very fortunate to have that passion combined with a career of education. And that all combined to make her very attractive to this project, because Vera Rubin is looking to utilize the data here in cooperation with educators across the country to bring real science to students. And hopefully she'll tell us a little bit of those efforts of hers, but I am really looking forward to hearing the story of the Vera Rubin, what it's capable of. We know that it's right there on the edge of science for us. So, Ardis, can you join us? She is not in Tucson today, but we've got her on Zoom.
Yes, thank you, Ed.
There she is.
Okay. Okay, can you see my screen fine? I believe so.
Yes, we can.
All right, thank you. Well, thanks everybody for inviting me to come and speak with you. I want to give you just a little bit about my background. I went to the University of Michigan as an undergrad, intended to become an astronomer. By the time I got out of college, I was a geologist instead. My aspiration was to go into planetary geology, but I couldn't go to grad school and I needed to find a job. So I went into teaching instead, thinking it would be just a short-term fix. Well, 38 years later, I left the career to come here to Tucson and take a job at Rubin Observatory. So in those 38 years, what I did is I primarily taught high school. I taught some college courses as well, astronomy, geology, physics, chemistry, worked in planetarium for about 30 of those years, part-time as my assignment, had an after-school club most of those years, and for 28 of those years, I had a club called the Rats, the radio astronomy team, and you can see a picture of one of our radio telescopes that we built in this slide. In 2017, I was hired by Rubin Observatory to design and lead the education program. Rubin is very committed to education and public outreach, so committed that the money was written in from the very beginning of construction so that we would have a fully fledged program developed by the time the data began flowing. So you can see one last picture here in the lower right was one of our teacher groups that we had up at Kitt Peak and here in Tucson for a week at Rubin Observatory, which is the building across the street from where some of you are sitting right now, and in Stewart Observatory. So I want to explain a little bit about how Rubin Observatory fits into the local and the national infrastructure. It's part of NSF Noir Lab, which is the National Optical Infrared Astronomy Research Laboratory. That is the building that sits right across from Stewart. Now, Noir Lab is a series of observatories that are all umbrellaed under that heading. And so we have the both the optical and the infrared observatories. And in particular, if you look at this graphic and focus your attention on the purple in kind of the middle bottom, because there's a lot of other things on this very busy graphic, you can see that Noir Lab has telescopes both in the Southwest United States, of course, Kitt Peak being the closest. We have the Community Science and Data Center, which is right here in Tucson, Arizona. We have telescopes in Hawaii. We have telescopes in Chile. The Rubin Observatory telescope is actually in Chile, but the headquarters is in Tucson, and that's where many of us work. So to give you a little context about where Rubin Observatory is, it's about 30 degrees south latitude, so it's very similar in latitude to where Tucson is, north of the equator. The altitude for Rubin is very similar to the top of Kitt Peak. So for many of you locals who have been up to Kitt Peak, you kind of know what the altitude is up there. It's very, very similar when you go to the Andes. You're in the foothills there. And you can see in this graphic that the nearest large town, of course, is Santiago, but Rubin Observatory is somewhat north of Santiago, and the smallest city near it is La Serena on the coast. Both Rubin Observatory and Noir Lab are funded by the National Science Foundation. Rubin in particular is co-funded by the U.S. Department of Energy Office of Science. And that is why when you see our official name in different places, it says NSF/DOE Vera C. Rubin Observatory. So that's our actual long official name. You can see in this picture on the right that Rubin Observatory has kind of an unusual shape for an observatory. It's built into the mountain. It looks kind of like a shoe or a boat, some people say. And the story of this observatory goes back 30 years, and some of it very local. So Tony Tyson from UC Davis was thinking about what kind of instrument that could be made to collect a lot of data, because we would need to collect much more data much more quickly than we were able to 30 years ago in order to gather enough information to understand the nature of dark matter and dark energy. At the same time, Roger Angel at University of Arizona was thinking about a large wide field telescope design. And you can see one of the early drawings of this so-called dark matter telescope. So momentum began building for an instrument like this. But, 30 years later, we're just about ready to finish construction. So it gives you a perspective that projects of this scale and really of this cutting edge technology take a long, long time both to develop and then to be financed. So why do we need Rubin Observatory? Well, most of what we know about the universe is that we don't know what it is. We don't really understand dark energy. We don't understand yet the nature of dark matter. Everything we see is only a very small sliver of the universe. And so to have an instrument like Rubin Observatory, we're hoping will really give us a foot up on being able to understand some of these long-standing questions. The early name of this telescope was the Dark Matter Telescope. every 10 years, there's a decadal survey that goes on where priorities are set for what is the most important instrument to be built in optical astronomy, radio, infrared, whatever. And in the year 2000, this telescope first came into the decadal survey prominence, and it was renamed the LSST, which, as you can see in the title, stands for Large Aperture Synoptic Survey Telescope. So the idea there was the large aperture means just what it is. It can gather a lot of light. And synoptic survey meant it was going to see a lot of the sky, and it was going to keep taking pictures of that sky over and over again. And to combine these qualities of wide images, fast ability to take these images, and to see very deep in these images, no telescope had ever done those three together at that scale. 10 years ago, we started construction. In 2019, it was renamed Rubin Observatory for Dr. Vera C. Rubin. Rubin was the first astronomer who provided convincing evidence for dark matter. She was an advocate for women and early career scientists in astronomy. And Rubin believed very firmly that anybody should be able to do science, regardless of what their position is. She treated everyone with great respect and empathy, and she had a persistent sense of curiosity for her entire career. We are proud to be renamed after Vera Rubin because we feel like we want to carry on her legacy of bringing everybody the ability to do science and to understand more about the universe. Now, Rubin worked at a time when it was difficult for women to do astronomical research. She was passed up for some awards, although she received many in her long career. And more recently, she has had a number of other objects named after her, as you can see, craters on the moon, a ridge on Mars, asteroids. You may have seen recently the Rubin quarter came into circulation. It began circulating in June as part of the Great American Women series of quarters. And there was even an episode in Star Trek Discovery where there was a nebula named the Vera Rubin Nebula. So she's been persistent in culture for a while, but this is the first time a major public national observatory has been named after a woman scientist. So let's take a look at Rubin Observatory. If you do a cutaway of the observatory, the dome you can see on the far left in this image houses the telescope. It sits on a pier. It is very robust in terms of earthquake protection and vibration suppression. The telescope is oriented into the mountain to take advantage of the prevailing winds, so there's the least turbulence possible. But what Rubin Observatory offers that some of the older observatories do not is kind of an all-in-one facility. So for instance, every few years we have to resilver the mirror. And in this case, you know, all we need to do is bring that mirror down on our vertical platform lift into the lower part of the observatory that you see on the right in this diagram. And we have the coating chamber right there on site. It also, the lower part of the observatory also houses things like the machine shop, the control room for the telescope. There's a clean room there for the camera or any kind of delicate instruments that we need to work on. So it's really an all-in-one facility. And that really speeds up the time we have to invest in being off sky, because we can do most of our things right here without taking any of the instruments or mirrors off the mountain. Now, Rubin Observatory is different than many telescopes in that it is a survey telescope. When Rubin was renamed for Vera Rubin, we had this previous name hanging around, the Large Synoptic Survey Telescope, which was hard even for some astronomers to say. And we had a lot of logos that said LSST. So we actually repurposed the LSST and renamed our survey the Legacy Survey of Space and Time, so we could make use of those logos still today. And so what Rubin is going to do, starting later this year, is begin a 10-year survey of the entire sky in 6 different filters, approximately 800 times. The entire sky will be surveyed over that 10 years. And this will result in, as you can see here, a collection of almost 40 billion objects. It's just a staggering amount of data. Now, when you think about or put that in perspective of where we are in when we say a survey of the southern sky, I wanted to show this map to show that we actually survey above the celestial equator also a little bit, to follow the plane of the ecliptic, because one of the things we'll be doing a lot of is solar system science. So you can see in this graphic, the main survey is in the green part. We have fewer visits along the Milky Way, but you can see that part as well. We have some very small spots called deep drilling fields. Those are places we're going to visit more often. And so every 2 to 3 nights, every 40 seconds for 10 years, every time it's clear, every time we can be on sky, the same pictures will be taken over and over and over again. And over time, they will be co-added together. Surveys are great for a few reasons. We can collect a lot of data that can be used for many different kinds of science. But in the case of our telescope, since we're going to survey the same areas over and over again, we're going to spot many changes that will happen in the sky, both on the time scales of hours and in time scales of years. Now, if you think about a survey like a jigsaw puzzle, imagine you just start working a puzzle and you don't see very much of the picture yet. As you build out that puzzle, the picture becomes more and more clear. And some patterns in astronomy are only emergent when you look at the very large scales of things. This is the case, especially when we're trying to think about dark matter and dark energy. So collecting survey data is sort of like working a puzzle. By the way, this is a James Webb Space Telescope image. I took this off the internet. They're selling puzzles. I hope someday we'll have some Rubin puzzles out there too. But what a survey also allows us to do is have the entire world to participate in making discoveries and doing science. It's really a paradigm shift from the old way when small teams or individual observers had telescope time and they did their own little projects. Now the entire world can be involved. So in the construction phase of Rubin Observatory, we have 28 countries involved already in contributing some sort of effort toward the construction, whether it was mechanical or software, et cetera. We also have science collaborations that are organized by themes of science that are going to be researched. These are open to everyone. And we have over 2,000 science collaboration members around the world. And so not only do we collect a lot of data, but we open that data for a lot of discovery by giving it to the world. Now, the 3 parts of Rubin Observatory that really make us unique and stand out are the camera, which is the largest camera ever built for astronomy, the Simone Survey Telescope, which I'll tell you a little bit more about, has a unique optical design and a very nimble mount, and then our global data system for transferring data. And we'll talk a little bit more about that as well. Putting these 3 together, we're able to achieve this wide, fast, deep idea of collecting data. The honeycomb mirror that is the primary mirror for the telescope, 8.4 meters, was built right here in Tucson in the Mirror Lab. And you can see a picture from the Mirror Lab here. I'm not sure of the exact date of this picture, but I know that the glass was cast in 2008. And the final polishing was done in 2015. So this was a long project And then in 2015, it was put into storage for almost 9 years until it made its way to the mountain. And just in the last 12 months has been turned into an optical surface that we can use. The telescope mirror itself is unique in the sense that it is able to have two different curvatures for the same mirror. The light comes in and strikes the outer surface first, bounces back to a secondary mirror, back to the inner surface of the primary mirror, what we call M3, and then up into the camera. And that tertiary mirror design is set up in a way that makes the telescope short and lightweight because it doesn't have to have a very long structure. The effective focal length of the telescope is 1.234. So that's an easy number to remember. Okay. Let me get back here into sorry. I wanted to mention to you that the mirror was shipped, first of all, by surface down to Houston, and then in a ship across to the west coast of South America. And then from there, was driven at a rate of 2 miles per hour-ish up to its final resting place in the observatory. And this is a tunnel that it had to go through in order to get to the observatory. And if you can see here, there's just a very, very small clearance on either side of this tunnel. I wanted to play a short video of in April, about a year ago, when we put the optical surface on the mirror. And I know this is a little bit of ancient history now compared to seeing the first look images, but I have to say this is probably one of my most favorite videos of all. Okay, 1 second here while I try to recover my presentation. Okay, sorry about that. Little bit about the camera. The LSST camera is about the size of a Mini Cooper. You can see it weighs about 3 tons, operates about -100 C, and it actually has 3 completely different cooling systems within that camera, depending on what part of the camera we're talking about getting cooled. The camera has 6 filters that can be changed in very quickly. Any one time, we have 5 of the 6 in. We tend to use the shortest wavelength filter during dark time and the longest wavelength filter during bright time. And so that last filter, the U filter or the Y filter, swap out about once every couple weeks. These filters were built and the camera at SLAC, Stanford Linear Accelerator National Laboratory. And you can see some pictures here of animations that they built and some technicians checking out the optical quality. This camera has the largest lens ever built. It holds 2 Guinness World Records, both for the largest optical lens and for the highest resolution camera for astronomy at 3.2 gigapixels. And so if you think of pixels as people, that's 3.2 gigapixels is greater than the combined population of the 3 most populous countries in the world. Because of this very high resolution, we're able to see details of and its great sensitivity. We're able to see details of very, very distant objects, but we're also able to pull out very, very faint objects that are closer, like near Earth objects. So sometimes when we think about high resolution, we immediately start thinking about, oh, we're seeing better, deeper, which is true, but we're also able to pick out details closer in because of this sensitivity as well. So it's a great combination there. It's designed to have a pixel size of 0.2 arc seconds. We really can do a little bit better than that in operation, but we're also limited by the seeing of the atmosphere. So, this is kind of our standard for where we're going to go in terms of our resolution. The camera images are very, very large, and I'll show you how large in just a moment. But just thinking about this, they're about 100 times larger than other typical telescopes that might have a mirror that size. And because of that, in 10 years, we can do what would take 1,000 years for another telescope. And this is, to me, one of the most exciting things personally, is that this instrument is going to help us speed up the rate of discovery in a way we've never seen in history before, not only because of the amount of data it can collect so quickly, but also because of the amount of people that will be researching and investigating that data. So if you think about the constellation Orion, visualize drawing a circle around the diameter of Orion's belt, and that's about the size of one image, an area effectively just a little bit more than 45 full moons. And so each 30-second image is that large. If you wanted to display one of these images in its full native resolution, you would need almost 400 4K HD TVs. Or to imagine how large that is, it would have to be a monitor a little bit more than half of a basketball court in size. So these images are just huge. And you can zoom way, way in on them to see things that aren't apparent in the zoomed out view. The Simone Survey Telescope is actually the name of the telescope that is inside of Rubin Observatory. It's named after the Simone family, who donated a large amount of money, along with Bill Gates, to get this telescope project off the ground. So it actually started with some private donations. And the telescope was officially dedicated and named this last fall. So it's a relatively new name. You may not have heard of that before. You can see in this wide angle picture inside the dome that you can see a wide mirror in the telescope, but it's also very short, as I mentioned before. And this short and squat ability allows the telescope to move very, very quickly. In fact, I'm told that when the telescope is moving at full speed, you cannot outrun it. I don't think we plan on moving it that fast all the time, but it has to have the capability to slew and settle to the next place in the sky within 5 seconds of completing its picture. Now, because almost all of the images are 30 seconds long, what that means is that the telescope is constantly moving. And because of that, we have what's called a crawling dome. The dome is constantly moving too. So the telescope will set up on one side of the dome, and over that 30 seconds, the dome is rotating to put it in optimum position for the next image. Because of that, when you look at the observatory from the outside, you'll notice that the slit, when it's open, is wider than a normal telescope dome, because it's taking advantage of this sky that it's tracking constantly. Now, combining all of these things, these wide field of view, the very fast ability of the telescope to move and take images, and this very, very high resolution camera, what it's going to allow us to do is, over the 10 years of this survey, taking the same pictures over and over again, we're actually going to create the ultimate movie of the night sky. So over the next 10 years, not only are we able to co-add the pictures together, but we're able to see all the changes in these pictures over time. I wanted to just take a minute and step back and tell you a few things that I thought about when I visited the observatory. I started working at Rubin in 2017, and just last November, I was very fortunate to be able to go down to see the telescope finally with the members of my team. I work for the Education and Public Outreach Department, and you can see some of my team members here on the left. Our team went down there together to meet with some of the education and public outreach people who are working in Chile, and also to tour the observatory. And one of the things, if you've been in a lot of observatories have a certain smell, a certain feel. I mean, a lot of observatories are very, very similar. But a couple things I noticed here: the telescope is very quiet, and the observatory is very clean, even though it's under construction, because everything is new, right? It's like that new car feel. So that was kind of exciting in itself. Now, when we were there, the telescope was under construction. So, we didn't see it in operation. We did see it move a little bit in a test move, but, it was daytime. It was not nighttime. And so I can't give you a lot of expounding on the marvels of this telescope at night yet. But I can tell you that it's exceeding expectations early on. And so we're all extremely happy about how things are going in terms of our progress. And right now, we put out our first look images. I'm sure you all saw them, or most of you have seen them. But we're still in that process of commissioning the telescope. So it's going to be a while yet before we begin the survey. I wanted to talk for a few minutes about data, because this is the part I feel like is so hard to communicate to most people. And that is how much data is flowing every night. So if you imagine this, every 40 seconds, we've generated a new 3200 megapixel image, which translates roughly to somewhere between 12 and 15 gigabytes. Every night, 20 terabytes of data. Over the course of the survey, trillions of measurements and billions of objects. So it's just a staggering amount of data, not only the amount of data, but how quickly it's coming in. And so if you wanted to collect just one night of data on your laptop, you would need about 40 of them. And because of that, science isn't done by downloading images and looking at images. A lot of this work is done in the cloud. We're looking at catalogs. It's not necessary to look at an entire image. And so it's also a paradigm shift in that way, where a lot of people are just like, well, I want to download the image and find things in it. But it's not realistic. Even if I tried to download one of those first look images that showed up a few weeks ago. And it was the image of one of the cosmic galaxy things. And my computer said it would need 3 hours and 45 minutes to download the image. But even when you have an image that big, how do you open it? A lot of the programs that we might choose to use would grind away for a long time trying to open it. I invite all of you, if you have not yet done so, to play with our image viewer on the website, because this allows you to go very deep into an image and quickly explore it instead of having to try to download something yourself. Just to kind of give you a routine of how this works, every 30 seconds, we take a picture. That picture is calibrated in a number of ways. It is sent around the world very quickly. In less than a minute, everything that has changed in that picture has been classified as an alert, and that's a public message sent out worldwide. We expect to get about 10 million alerts per night once the telescope goes into operation. Within about a day, databases of all those objects in the images will have been cataloged, and within a number of days, available to those who have data rights to access them. To show you just a graphic of how this works around the world, the data first starts out on the mountaintop at Cerro Pachón. It goes to La Serena and then to Santiago. From Santiago, there is a redundant fiber optic network that travels on either side of South America. Two 100 gigabyte per second lines come to the United States, ending up at SLAC National Accelerator Laboratory. SLAC is the place where the alerts get generated, and it is also then sent across the Atlantic to data facilities in France and the UK. Not only are those facilities helping us with processing the data, but also, also the long-term storage of that data. I'd like to talk a couple minutes about the science of Rubin Observatory. We have 4 key areas. One is the Milky Way, one is dark matter and dark energy, the changing sky, and the solar system. And I've mentioned a little bit about the changing sky before, but we're being able to do these surveys with following up on all sorts of objects that have either changed in brightness or have moved in the time frame that we've looked at things. Not only short changes, but long-term changes as well. The way we tell the difference in how things change is by what we call difference imaging. And in difference imaging, what we do is we have a template of the sky, the things that never change, and then we're able to pick out the things that do change, whether that's like a flash, like a supernova, a moving object in the solar system, a variable star. And these alerts then are, generated and sent out world public, as I mentioned, almost immediately. And so that's one really big key area of our science. Another one that we've mentioned is dark matter. I saw somebody in chat mention, didn't Zwicky come up with the idea of dark matter? Absolutely, he did. Rubin was not credited with the discovery of dark matter. She was the scientist who put forth decades of research that convinced the astronomical community that dark matter was a thing. And so that's Rubin's contribution to the science of dark matter. We know very little about the Milky Way now compared to what we will know 10 years from now. And so we're going to gather a lot more information about not only stars within the galaxy, but also our local environment, stellar streams, dwarf galaxies. And that will help us answer some of the big questions about how the Milky Way formed, a little bit more about our solar neighborhood and the kind of place we live, the stars that are nearby, what they are like, and also just the bigger picture about how galaxies in general form. By the time our survey is done in the first 10 years, we expect that we will quadruple the number of solar system objects that we will find. Some of those very interesting areas are, the near-Earth objects, potentially hazardous asteroids that are sometimes real buggers to see because they're so small and they're so dim. But also thinking about, is there a planet 9 out there somewhere? Our telescope is probably the best instrument in the world to find it if it really exists out there in the outer solar system. So there's going to be a lot of really neat areas of solar system science. And the solar system discoveries are going to come relatively early on in the survey because some of those other sciences need a lot of data to be able to start really making some major shifts in understanding. We're also going to be a follow-up facility with other observatories that work across the electromagnetic spectrum and also things like LIGO that does gravity waves. So when there is a gravitational wave event, LIGO can identify an area of the sky, but not an exact place. We have the ability to pivot out of our automated scheduler with a very short amount of time to look and see if we can find something there, or if we maybe are looking at that place at the time of the gravity wave event, and then be able to relay that information more effectively to all the other follow-up facilities around the world. So that's what we call target of opportunity mode. When these strange things happen, we're able to pivot very quickly and be able to change things from our observing program. But I think one of the things in conclusion that scientists are really excited about are the new things that we don't know about, the weirdo things that are going to show up. And we're going to say, what is that? The pieces of data that make us rethink our current ideas about our theories. And so we're going to have a lot of those aha moments in the next 10 years. We don't know what they are yet. We don't know when they'll come. But I think all of us believe that they will happen, and they will happen with a great number. Many of you saw this cosmic treasure chest image that was put out on the first look day on June 23rd. And this image was actually made from 1,185 single exposures in 4 different filters. And in this one image, we have about 10 million galaxies and 1.5 million stars. Now, zoomed out, you don't see them all, of course, and you can't count them. But if you haven't played with that sky viewer yet, I encourage you to just keep zooming in, and be patient and go deeper and deeper. And you'll be amazed at the number of things you can see there. This image that we put out for first look represents a survey depth about halfway through the survey. So, in normal operations, we're taking a couple images of an area a night. In this particular case, we took over 1,000 images in the course of 1 or 2 weeks and added them together. So you're able to see a lot more detail, but it still is not as deep as it's going to be at the end of 10 years. So I just wanted to mention that if you'd looked at this image and played with it. And you may have seen this also in the first look press conference. This is the annotated version of that image. And most of those things that are not annotated have not been named yet. Now, many of them have, but not all of them. And so a lot of those little speckles, they're out there waiting for names and waiting for information. You also probably saw the number of asteroids we detected in just 10.5 hours of looking at the sky. And so as of a few days ago, almost 1,900 new solar system objects were discovered in those very short number of days. We only discover about 20,000 new asteroids a year. So in 10.5 hours, we did like almost half of a year of discoveries of asteroids. And so this is what I'm talking about, where we're really going to accelerate the number of discoveries. Our very first citizen science project went live last week. It's called Comet Catchers, and it's using the data that was gathered by Rubin's commissioning camera last fall. So if you are interested in citizen science, I encourage you to go to Comet Catchers and try it out. It's really a fun project. I did some cruising around on it a few days ago. A lot of people are asking, I'm an amateur astronomer, how can I get data? Well, it depends what you want, and that's a longer conversation. But these alerts, these changes in the sky I mentioned, can just through, and all to do serious data work, you need to have data first of all. So generally, you have to be a scientist in the United States or a researcher, someone that's part of our communities. You have account the Rubin Science platform, and then you can work in a very technical way to access data. But all data public after 2 years. Now, if you're an amateur and you want to find out like what are the asteroids you might be able to see or the supernova that are rising in magnitude, what you can do is go to these community brokers. Community brokers are software systems. We have about 9 of them identified so far. Help you filter out just what you want to look at, certain magnitudes, certain area of the sky. And even having said that, you're going to have a lot of data. And so just be prepared that if you want to access one of these brokers and take the time to learn how to use it, you're still going to have a lot of data. And the other part is important to understand what it's capable of doing, right? So, I mean, I know my telescope can easily get to magnitude 17, but I can't get to magnitude 20. And Rubin is saturating at 17. And so the really good data is going to be out of the reach of a typical amateur instrument. I can talk more on that later if you have specifics. I want to wrap up because I realize my time is running short here. I just wanted to mention that as I said a few minutes ago, I'm part of the education and public outreach team. I'm happy to entertain your questions, but be kind to me. I'm a teacher. I'm not a scientist. But what our team does is we're the ones charged with being the public face of Rubin. We're the ones that you communicate with when you have questions. We're the ones who have built the website. We do the social media. We design the games. We do all of these things in terms of communicating with the general public, but also the education program. And so all of our investigations use data that are right now coming from other observatories and surveys until our data begins to flow. But we have these free interactive investigations available for you to use. They're very friendly. They don't require any special preparation. They don't cost any money. They're available in English and Spanish. And if you're a teacher, they come with a lot of support materials, from teacher guides to assessments and phenomena, many other things. We've designed these to be dropped into anywhere you might teach astronomy. So they're designed as a lesson that will be 2 to 3 hours in length. And we also provide teacher training and support. So if something's going wrong with something you're using on our website, we're there to help you. We're there to do professional development, and we do a lot of that in terms of teacher training. And I just wanted to show that these are the 7 investigations that are available right now to you. They were chosen based on what teachers said they needed the most and what we could deliver the best. Lastly, what our education team has been doing for the last half a year at least is designing first look resources. So we have a special page under the education section of Rubin Observatory that has first look resources on it. We have tours of the image where you can learn more information about different objects in the images. We have Rubin Bingo, a Rubin coloring book. We have other kinds of first look materials like estimation and scaling activity, so mathematical activity. So if you do any outreach or this sounds like something you might want to share with a teacher, please direct them to this page because we've got a lot of new cool stuff on it. So this has been a big month for us. On the 23rd of June was our first look. A week later, we released our first data preview. And so people are now working with some of the very first preliminary data that was collected by our commissioning camera in the fall. And the big question everyone's asking is, when does operations start? Well, we don't know exactly because we're in commissioning, but we're hoping sometime late this year. After we begin collecting data, it will take us a year before we can do a data release. We'll collect 6 months of data, we'll process that data for 6 months, and then it will be available about a year after we begin collection. So right now in commissioning, what we're working on is getting to know the telescope, making minor adjustments and tweaks, doing a lot of verification of how well it's performing, preparing different kinds of systems for the onslaught of the real data coming through and making sure everything's just right. So this takes time. Every new instrument has new surprises, but I can tell you in general, things are moving along nicely. I think we're about week 12 right now in commissioning. And so this will go on for some amount of time until all of our performance verifications are satisfied. We've figured out all the little things we want to figure out before we start the main operation. I want to close with a quote from Vera Rubin, which I really like. Shoot for the space in between, because that's where the real mystery lies. So I want to thank you very much for allowing me to speak with you tonight. I'm happy to entertain your questions.
Wow. That is a lot of data. We have questions in the room. Let's start in the room. We'll get to questions on social media in a while.
Yeah, it's been a horrible disaster for all of us that the president's minions have been cutting the astronomy budgets in half. I might guess that Vera Rubin Observatory, by its very name, is going to get more than its, well, share of the brunt of the disaster. Do you have any comments on how Rubin Observatory is weathering or going to weather the oncoming disaster?
Well, right now, everything's fine. None of our funding has been affected yet. Every day is a new set of questions. And I think, realistically, we really don't have a clear vision of how much Rubin will be affected in terms of operations until sometime later this year, when everything gets settled by Congress. And even then, I think, most of our funding is going to be intact because we're the big main new science project in town, so to speak, or on the globe. So it's certainly not like we're going to get shut down, but as all the other agencies are being affected, there will be some amount of belt tightening. How much, we don't know yet.
Oh, we have a question here in front.
Actually, I have two questions. My first question is, do you have any kind of a system on the telescope, like adaptive optics or anything like that, to help out with your, with the going through the sky?
Yeah, we have not adaptive optics, but active optics. So, adaptive optics requires lasers and stuff. And because of the nature of our telescope, we can't have that kind of instrument. But active optics only demands that you create basically elaborate lookup tables that will predict the deformations and strains that gravity will induce on your dish as you move it around. And so we do have adaptive optics both on M1, M3, and M2. I think on M2. Maybe I might be wrong about that, but definitely on the main mirror, I know we do.
Okay, and my second question was, when I looked at that image of all the millions of galaxies that you showed, it looked like a lot of them were double images, like two spots. Can you go back to that slide?
I can go back to it. It might take me a minute, but I will do that. So are you talking about the one that was annotated?
No, no, the one
Or
that wasn't annotated.
the one that was at the very end with the quote on Rubin?
No, the one that was
The
right
one that
before.
was, okay, I know which one you mean now. Okay. Now I need to share my screen again.
I'm sorry.
No, that's okay. So this one, I believe you're talking about.
Yeah. It looked like many of the items in that picture looked like two spots.
I don't know. I don't see that pattern. I see lots of things. And you know, I will tell you the first time I started playing with this image in Sky Viewer, I didn't realize that you could keep zooming in. At first, I just zoomed in and everything looked kind of pixelated, and I was like, oh, this is the end of it. But then if you wait a number of seconds, it stops being pixelated, and then you see more things that you didn't know were there. Um, and so you can go in at any scale you want. I don't really see the pattern you're talking about as doubles, but I will tell you there's a lot of fascinating things in this image if you take time to explore it.
There's a lot of objects, I'll give you that.
Oh, by the way, I didn't mention, but the cosmic treasure chest image, the first one that came up when you go to the web page, that's 24 square degrees, which is about 2.5 Rubin pointings. So every one of our pictures is about 10 square degrees.
Any other questions in the room? Oh, we got one in the back. A question. You mentioned the event. I'm sorry, the data release would be in late 26. And it would take about a year to put that together. What about the event notifications? Aren't those like immediate?
Yes,
So
they're immediate.
when would they start? And are they available to the public?
They're available to the public, world public, anyone. We don't know exactly when the alerts will start. The alerts are probably going to start in a small amount before official operations, but when that is, I don't know.
Okay, well, my question was that I wanted to say congratulations. There's a lot of tools for the non-astronomy community for teachers, so that is just phenomenal. So my first question would be, the picture that was on there of the educators that were there at the telescope, is that just the team, or is there a lot of other people that develop these tools for educators, the non-astronomy community?
No, it's just a few of us because our entire EPO team is about 10 people. And we're kind of like one of everybody. So I am the token teacher. There's a graphic designer, there's a data scientist, there's a manager, there's a social media person, a communications person. I lead a very small team of people called the education team. It's we have our data scientist that participates. We have another education specialist that works with us 25% of her time. We have a consultant from Stewart Observatory, Ed Prather, who works with us a couple hours a week. But really, it's a very small number of us doing this work. And that's why people want a lot of things, but it requires a lot of time to get them done when there are only a few of you doing it. And we have, a few developers too, but since our entire delivery is online, everything depends on our developers too. And that time has to be divvied up among all of our projects.
Well, again, congratulations, because that was a small team of people. That's what my question was. That small team of people developed all these educational tools, and I'm grateful.
Thank you.
And I have one quick question, another one about the annotated one that you had up there, the unnamed stars or objects. Who names those objects that are not named?
Well, the International Astronomical Union has a lot of naming rights. The Minor Planet Center deals with a lot of things regarding the solar system in particular. One of the questions we have had a lot is, what is going to be our survey prefix? So if you're familiar with like amateur astronomy, NGC is the new general catalog. You might know ZTF. You might know IC, some UGC, you might know some of these prefixes. So the question is, what is Rubin's prefix going to be? And I believe it's going to be LSST for some of the survey, but I was told recently by a scientist that certain types of objects might get their own survey prefix designation that is different and unique. And I don't know what that is. But, realistically, we can't like just pick names and name things after our kids or whatever, There's a very orderly process that has to be approved by everyone. And so the names will end up being somewhat unimaginative, like the ones you see here.
Hi, first I want to thank you for the little tip about when you're looking at the viewer and you see the pixelated view, because I noticed that and it's like, now I just realized I have to be more patient and wait for it to clear up. So I was invited to go to the opening a couple of weeks ago here at the U of A, and I didn't ask the question, and maybe I should have. It seems like with the success that you're seeing almost immediately, that you'd want to have a similar telescope in the northern hemisphere to be looking in that direction as well, especially when you looked at the number of asteroids or that are floating around, and it was amazing to see that. So it seems like it's a really strong argument to continue even stronger science.
Yes, a lot of people have made that comment. The reality is nothing's planned. This telescope, to put it in perspective, started 29 years ago, right? And it took a long time to even get the funding to get it into construction, and we're still constructing. So we don't have a plan for Rubin North, if you will. However, I will say that the science we're going to learn from our Southern Hemisphere survey can be applied to the universe as a whole, right? I mean, not specific discrete discoveries of objects, but what we will learn from science. I think we can apply regardless of where that telescope was built. Another question that comes up a lot is, what are you going to do after the first 10 years? And I'm sure there are people thinking about that, but I'm also sure that there's not a specific answer yet. We don't even know what the technology will be in 10 years, right? I mean, that technology changes at such a fast pace. And depending on what we find out this telescope is very good at doing, that might also bias the technology toward a certain type of work. I don't know. I'm speculating. I'm not speaking with an official voice of the observatory here, but I think there's a lot of latitude in what the next 10 years will be after the legacy survey of space and time is done. Certainly the telescope will still be a youngster and will have many good years of service left.
Any other questions in the room?
So Ardis, we do have quite a few on the chat for Zoom. Do you want to just read those or do you want me to? Do you want to just read them and answer?
The first one I saw was about Zwicky, I think, and I answered that one. Richard Spitzer, how dependent are you on NSF funding? That's pretty much our lifeline. Like I said, we're half funded by the NSF, half funded by the Department of Energy. Both of those departments are experiencing funding reductions. So very is my answer, very dependent. There's a question about, is there a dormitory for the folks that work on site? There are quite a few people that come up every day to work. A lot of them are bused from La Serena. So, they get on the bus early in the morning. There's a cafeteria up there. They work their shift. They come back home at night. If they are working like an overnight shift, like the telescope operators, some of the people who have to be there for engineering or site purposes, we do have a dormitory on site. It's a relatively small dormitory because most people do not have to spend the night up there on a routine basis. But there is a dormitory there. There's a cafeteria there. Is the telescope operated from Tucson? There is a control room in the building across the street from Stewart in our lab. But the telescope is operated from the summit. So there are actually people there physically every night operating the telescope. It doesn't require a lot of people, but there's always a crew right there at the summit operating it. Let's see. Then Peter, you have a question about the diffraction pattern in the Rubin Observatory images. If you've looked at the diffraction pattern of stars in the cosmic treasure chest, you might have noticed a couple things that maybe you didn't expect. One is that they're multicolored, and one is that there's a whole bunch of them. It's not just like a symmetrical 4-spike or 3-spike pattern. You may already know what the reason is for that. When we take these images, we are dithering, we are rotating, so the images aren't always taken at exactly the same angle. And because of that, the diffraction spikes will also rotate. Because images are taken in different filters that are then assigned different colors, the spikes in those images will be different colors based on what filter was being used when that particular diffraction spike was imaged. I don't know if that makes sense to you, but multiple filters over multiple images and multiple rotations. So it's not a characteristic pattern. I will say it's a very pretty wild pattern. That's all I see in the meeting chat. Do we have other questions?
Terry may have some on social media.
There are none on social media.
I think I exhausted everyone.
No, we're amazed. Ardis, thank you so much for bringing this to us.
Well, you're most welcome.
We'll look forward to seeing you in the room next month. We can ask all the questions we forgot to ask tonight. Thanks for joining us. Okay, Eric. Dr. Kokoschka is back with us tonight. As you know, Dr. Kokoschka shares with us the planet report each month, and his blog appears on the website. So as you try and remember when you're going to go out later in the week to do some observing, you can also see his comments there.
Yeah, I'll give you the view for the next 2 months because I won't make the next meeting. We have one evening planet that's Mars, and it's getting lower in the west, and by August, by end of August at least, it's getting quite low, so it's not too interesting anymore. and it's getting to the far side of behind the sun, but it still takes half a year before it gets in conjunction. So it's just a slow planet. And then Saturn rises around midnight right now, but within 2 months, that time will go forward to 8 p.m. And so it will become then a really good evening planet, at least for the late evening. And what's special about Saturn right now is that the rings are really faint and thin, because the Earth went to the ring plane in March and then the sun in May. And so it's just a couple of months that the sun went above the ring plane. It's still less than 1 degree illumination from the sun, and there's just not much light on the rings. But they are definitely visible if you have a good telescope. And it will be quite interesting in the next half year. Saturn will become even better in the evening sky, and the rings will change. They'll get brighter, but then towards the end of the year, they get very, very thin. Then the next planet to rise is in the morning sky, Venus. It's a really good morning star. At 3 a.m. it rises. And then over the next 2 months, it will be always about 20 degrees high when dawn starts. And so that's kind of the best months of the morning visibility for Venus. It's already past the greatest elongation. That means it's already more than half illuminated, and it's getting smaller, so it's getting on the far side of the orbit. And then Jupiter rises at 5, so that's not much before the sun. It's hard to see in the next week or two, but by the end of August, it will be rising at 2 a.m., and so then it will be up quite high when dawn starts. And so if Venus rises at 3 and Jupiter goes from 5 to 2 a.m., they must cross each other. And that's actually on August 12th, when they rise at the same time, and they will be at the same spot in the sky. Well, 1 degree apart from each other, but that's pretty close. So it really is worthwhile to get up on August 12th in the morning and see that just at the beginning of dawn, to have the 2 bright planets right next to each other. If you wait a week to the 20th of August, then you'll get also the thin crescent next to Venus. Jupiter will be a little off, but still only a few degrees off, so it will still be interesting. And then Mercury isn't visible within the next weeks, but then starting August 13th, it will start a good morning visibility, short one because it only lasts till the end of August. And it's not too far from Venus and Jupiter at that time. It will be 15 degrees below Venus. And so it's really easy to find in the second half of August. Just go from Venus 15 degrees down, and there's no bright star, so you can see Mercury. Uranus and Neptune are in the morning sky. They'll be better visible later in the year. But for Neptune, it's interesting to note this year, during this opposition period, right now, Neptune is only 1 degree south of Saturn. So you have a planet that's guiding you to finding Neptune. And so it makes a triple conjunction between Saturn and Neptune. You probably have to wait a few decades before that happens again. The next time it's possible to happen would be in about 40 years, when Saturn just makes it a little more around. But not every time there is a triple conjunction between 2 planets. So it may not even be the century that happens again. So if you want to see it, you need to watch during this opposition period. Right now, they are next to each other and both close to stationary, so it doesn't matter what day you pick, they are always close together now. A minor planet is in the evening sky, the brightest minor planet, Vesta. It's about 7th magnitude. visible in binoculars. Always in August is the Perseid meteor shower. It peaks around August 12th, but a week or two before and later, you still can see them. And if you look in the evening, they are really long tracks because the angle of impact on the Earth atmosphere is very shallow. But if you look then in the morning, you get a lot more meteors, but they really is very short, just fraction of a second for the fainter ones. And they're really fast ones, so 70 kilometers a second. Unfortunately, on August 12th, the moon rises not too much after twilight ends, so you only have a really dark period, short one. But yeah, you even can observe a day or two later, and then the moon will rise much later. So that's for the planets. Thank you.
Thank you, Eric. Yes, Brad, you have a. You should, yes. Brad has an addition. Okay.
Yeah, for planets, I would like to alert everyone to the view on the morning of July 26th. On the morning of July 26th, as you look out over the eastern horizon, Venus will be there, as we've just heard. And Venus will be just a little bit to the northeast of Zeta Tauri, which is evocative for everyone. Venus will be passing close to the Crab Nebula. And Venus will be, well, about as bright as the Crab supernova was at its peak. And the position of Taurus and Venus and Zeta Tau in the morning sky will be basically the same as it was when the Crab was at peak on close to July 26th, 1054. I've been waiting for this for about 4 years now. And so what we have on the morning of July 26th is a recreation of the sky at the peak of the Crab, which, by the way, was not observed by the Anasazi. That thing up at Penasco Blanco, that was not the Crab, although all our textbooks say so, but there are technical reasons we know it perfectly well was not the Crab. Nevertheless, the Anasazi and the Hohokam did see the Crab, that's for sure. They might not have left any records of it, but they saw it. But we can go recreating it by just stepping outside and looking at the morning of July 26th. Be there.
Great. Thanks for the reminder. That's a interesting thought. It would have been hard to miss if you were an observer of the sky, which in 1054, people were observing the sky a lot more than they do today. Great. Okay, I think with that, we're going to say goodbye to our friends on social media. Thank you for joining us.